We are Team 24 and this is our interim presentation. Our project focuses on a produce slicer. This product will allow both commercial and home cooks to cut fruits and vegetables more efficiently. The body houses sharp blades and the user pushes on a handle to slice the produce. The blade configuration can be changed to enable either horizontal slices or bâtonnet cuts.
Here is the exploded view of our produce slicer. We have 13 components excluding fasteners. The blades fit in the blade tensioners inside the blade housing. The other set of blades here is called the push plate and it sits on the guide plate, which also has a handle attached, which allows the whole sub-assembly to slide on the slice board.
The primary customer is anyone who wants to cut produce more efficiently. The secondary customer is someone who would also like to make bâtonnet cuts. Here is the functional analysis. The primary function is to slice produce. There are a number of functives here that describe how this is done. For example, in order to move produce, you have to add velocity and support the produce. In order to add velocity, you have to transfer energy from the user and limit resistance in order to enable the movement of the push plate.
We decomposed the slicer into three main parts and identified two feasible assembly sequences for this slicer. The first assembly sequence started from the base frame assembly, then we assembled the pusher part and the blades part respectively. The second sequence started the same from the base frame, then changed the assembly order of blades and pusher part. After that, we analyzed these two sequences and identified that it's more convenient to assemble the blade slicer with fixed pusher part, because it could be difficult to correctly assemble the sliding pusher part with installed blades. So we realized that the first sequence is more relevant for our purpose.
This is a function component mapping matrix, where all fasteners are excluded. We can see each function contains less than 40% of the total parts, which confirms our fast diagram is good. And each part has at least one function, so there is no redundant part.
This is the bill of materials for the produce slicer. The different manufacturing processes involved were die casting, sheet metal working, machining, and injection molding. For the processing time, die casting and sheet metal working was on the order of magnitude of seconds, injection molding was 2 minutes, and machining was on the order of several minutes. Assembly time was obtained from using the charts we learned from class for manual handling and insertion. The total cost of the produce slicer was approximately 59% of the retail price. Interesting to note is that from looking at online prices for catalog replacement parts of the produce slicer, the most expensive items from the catalog were die-casted parts, but they were some of the cheapest items from our cost estimates. These were the values that were used for the various manufacturing processes for operating cost and tooling cost. This is the quad chart for DfM. As you can see, all the components of the produce slicer are of high importance. The cost estimates for each component are ordered from highest to lowest on the right, and the slice board, guide plate, push plate, blade tensioner, and blades are the highest cost and should be redesigned for DfM.
According to function differentiation table, switch cut pattern is the one to enhance the slicer to satisfy the needs of different customer group. And from the function component mapping matrix, blade and push plate are the only part associated with this functionality, so they will be the differentiating modules.
The differentiated product has two modules, the blade and the pusher plate. Here you can see the difference in blade designs. The top cut pattern is a slice and the bottom is a bâtonnet. Slicing uses one blade repeated in an array, while the bâtonnet uses three unique blade designs in the subassembly. The blade modules use a common interface with the produce slicer via the blade tensioner, which holds the blades in place by two dowel pins and secures with 4 screws against the blade housing. The second module is the push plate. Here you can see the difference in push plates between the slicing plate stack-up above and the bâtonnet plate stack-up below. The push plate module interfaces with the guide plate using 2 screws which locate and hold the plate stack-up in place.
In case of the absence of the slicer part variation, the original family assembly diagram seems to be step-by-step sequence without any product differentiation. The feasible assembly diagram For modified product, almost the same as for the original slicer, but here we have 4 new components. The first one doesn't add as a differentiation to the product family assembly diagram and could be used with both blades sets. Next 3 parts are included into the blades part and add this differentiation. In case of the blades part variation, we have 2 types of final product.
This covers the produce slicer interim presentation. We are group 24. Thanks for listening.